the Stemler academic hour, and therefore it's supposed to start 10 minutes late. And let me remind you why you are all here. I was trying to convince you or explain to you why description length works and how that we actually do the calculation to get it to do what it does. That's the equation. And there's several terms I have to justify. Log sum of squares error, something to do with, well, that's just to count the number of parameters, something to do with the precision of the parameters, and some extra bits on the end. And I got a couple of questions following on from part one. Effectively, if I can misquote Sampson, what the hell is that L anyway? Right? So first of all, there's an L star that pops up somewhere else. That's different from L. Okay, L star is a particular specific thing. L is the code length of something. Right? Minimum description length is the minimum code length of something. It's the minimum code length of the data given the model. Right? So the whole idea is I've got some set of data that I'm going to transmit to you. So I'm going to send my data to Jesse, and I can either write down all the numbers and throw them at him one at a time, or I can tell him what the model is and tell him what the model errors are. And the idea is that if it's a good model, doing the second thing will be quicker in terms of code length than doing the first thing. So there are basically two terms that you have to worry about. LE, the description length of the model errors, also written as LY given M, that is description length of the data given the model. The description length of the data given the model is the errors. Right? If I've got the model, then I don't get to Y, I just need the errors, so it's the description length of the errors. The second term, LM, is the description length of the model, which I also write as L lambda, because lambda is my vector of all the model parameters. Right, so I'm going to assume that before I try to give Jesse my model, we've decided what the model class is, so that I don't have to describe to him what a radial basis function is amongst all possible classes of models. I'm just saying radial basis function, here are the parameters. Here are the parameters. Here are the parameters. So that's the basic idea. And there will be an optimum value where the decreasing cost of the model errors is offset against the increasing cost of the model if I plot the two as a function of model size. Okay. So you missed this joke last time, Dave. Occam's razor.
Yes, Thomas.
Sorry?
What word did you use? Thomas what? Hammer, was it?
Yeah, well, I went with mallet because I figured this sounded better. Okay, so that's the basic idea. Then I introduced a lot of this stuff following on from the fourth year unit, just for those of you that got through the fourth year unit, so you could see where all those pieces were actually needed. And so all of that stuff essentially was to derive two expressions. One is that if I want to describe some data, forget about the model now, but just data as a sequence of values, then the code for that is bounded by entropy, right? So the entropy of the probability of those values occurring. So if I've got some values alpha 1 to alpha n, which occur with some probability p1 to pn, then I can work out the entropy of that sequence, and that gives me an estimate of the most efficient code. So that's description length of a code of a bunch of numbers is just entropy. The second bit was, okay, what if I actually think about encoding a particular number where I don't have some probability distribution to build off of? So I want to have what is the most efficient way to code an integer. Right? And that's where we need to talk about self-delimiting codes. So I need to have a way of expressing a particular integer, and to do that I could send you the code for that integer, which is a sequence of bits. But first I need to tell you how many bits I was using to encode that integer. So I need to send you that integer, which is the length of the code for the first integer. But then before I send you that second integer, I need to send you the length of the code for the second integer, which is a third integer, and so on and so on and so on. So I've got some way of encoding an integer, and it takes log 2 bits. But I need to first tell you that I'm going to send you a code word of length log 2. So that's another code word of length log 2. And so on and so on and so on. And this can be actually operationalized. You can write code to do this, and it produces a unique sequence of bits which is self-terminating for every positive integer, and it's an optimal shortest code word for integers with no other a priori on them. If I can do an integer in that many bits, then I just need to add one more bit if I'm going to, sorry, positive integers is that many bits, then all integers is just one more bit to give you a sign. Don't worry about 0, that's just do the Hilbert's hotel problem to solve the 0. Once I've got integers, I can get floating point numbers by representing them as floating point numbers, and that just gives me a sequence of n bits and a mantissa, the m, which is an integer. The integer m is fine. That's, although we could encode the integer m with that L star that was on the previous slide, we actually just use a fixed cost for it because they're all about the same. Generally, the parameters are not going to be many orders of magnitude different from one another. Right, so a fixed cost is fine. That leaves us with the problem of choosing n, the number of bits to use to specify a particular number. And although I don't solve that problem here, I say, well, that number of bits n, I can think of it as the imprecision. Credit to Jack Moore for pointing this out. A better name for what we call precision is actually imprecision, because when delta gets larger, that means your numbers are less precise, not more precise. Right? But I'm going to call it precision because that was what Kevin and Alistair did, and it's their fault, not mine. But this precision parameter tells me how many bits I need. It's the error in my number. Right? And the way to think about that is I've got a model, I'm specifying the parameters of the model, but I don't need to specify those parameters to infinite precision. At some point, I can stop. I've given you enough information to reconstruct my errors. Additional data is not needed to build a model that's good enough to get the errors that I require. Yeah? And so we need to have a way of calculating that precision. How many bits do we need to specify those numbers? And that's what I'll hopefully get through explaining today. And of course, yeah, if you talk about a real number, well, a real number is just something close to a rational number. And so that gets us back to this expression here, which is I want my description length of my data, which is going to be the description length of the data and my model parameters. I'm going to call the vector of model parameters theta here. It's a change in notation which I'm going to justify because the lambdas are formally the weights of the basis functions. But there are a couple of other extra parameters to worry about, particularly the initial conditions. So the general set of parameters is actually a bit more than just the lambdas, and that's why there's the lambda theta thing. we're going to assume that if the model's any good, then that distribution of the errors is A, got mean 0, and B, because it's more than 30 numbers, we're going to assume it's Gaussian.
So then,
that's the law of large numbers, right? If you've got more than 30, then it's normal.
And then H here is the optimal code of that distribution.
H here is the entropy. So the entropy of that probability distribution is the length of the code. So the optimal encoding of numbers drawn from a Gaussian distribution is the entropy of that Gaussian distribution, plus 1. But if that worries you a little bit, it's just a negative log likelihood, which people like Sampson will hopefully be happier with. But, yep.
So we're trying to basically find an optimal way to represent a bunch of numbers.
Yep.
Is the self-delimiting code optimal?
Yes.
Right.
For if you're trying to send integers without any other prior on the integers. All right, so if I want a code that can send you any integer such that sending those integers will be in general short as possible, then that's optimal. If I've got probability distribution on those integers, right, and I know that that every integer I send is going to have a 50% probability of being 2 and a 50% probability of being 3, then I can get a shorter code. But if the task is just to send a sequence of integers, then the self-delimiting code is on average better.
Right.
Okay, is everyone done? Yep. So this is the errors of each point in my time series. So for each point in my time series, I'm making a prediction and I'm getting an error. The length of the code for each of those errors is entropy plus 1, and because I've got a time series of length n, I've got n of them. This term relates to the cost of the errors. The length of the model doesn't enter that directly, except that if I've got a bigger model, that model will be better, and the errors will be coming from a different, hopefully smaller distribution. Okay, so the L of E is going down with model size because the model is getting better and the errors are getting smaller.
But the fact that the errors are getting smaller, you mean that the variance of the error distribution is getting smaller?
Yeah.
You're not counting the actual amount of the error.
Because the task is to transmit the numbers in the data to some fixed precision, I want to describe my data x to 3 decimal places. What I mean by the errors getting smaller is that I'm using fewer of the decimal places that actually matter for the errors because the model is capturing more of the rest of it. So if I don't have any model, then my error is my data, and I have to specify the data. If my model captures the first 2 decimal places, then my error is just the last, in this case, 1 decimal place. So as the model gets bigger, the amount of mistake that the model is making is getting smaller in absolute magnitude compared to the previous model.
Yes, but if the absolute value of the error increases, does it mean that the L star for describing this number, a very small number, is less than?
So this is not L star. So L star comes in over here for the parameters, not for the error. So the errors are being drawn from a probability distribution. So I've got 2 different sorts of numbers I'm trying to deal with here. The model errors, which I'm modeling with a probability distribution, and so describing the cost of sending those model errors using a probability distribution. and the parameters of the model itself, which I'm saying I don't have a prior distribution on those parameters, but I need to specify them to some fixed precision. So the model errors, yes, they get smaller and smaller and smaller, and I care less and less and less about needing as many bits to specify them. Whereas the model parameters, they don't get smaller with the model size. In fact, we get more of them. Okay, so this is that's the LM term, that's the LE term. So the LE term is going down with model size K because the errors are getting smaller. The LM term is getting bigger with model size K because that sum's getting bigger.
What we're confused about was when we increase the model complexity, your error increases,
Yep.
your distribution looks more and more like a point mass, and that has lower entropy. That's why LE goes down.
Yep.
And then L is different from L star. And
Yes.
L is kind of like our optimal guess for this kind of. L
is the actual length of the code, and we're going to try and make an approximation to that, a good guess of it.
But then L star is like the actual.
L star is an actual computation, is that actual function, that sequence of logs. L star and L are completely different things, like opposite ends of the room. Again, don't blame me, someone else's notation.
Are you going to explain how you would operationally do that LE term?
Yeah,
Okay, cool.
yeah, it's coming. Are we happy with this one now? Okay, so a little bit of operationally, what do I need to do? Well, if I assume some particular probability distribution here, then that's just negative log likelihood of that probability distribution. That probability distribution, if I assume it's Gaussian, then it's negative log of e to the negative error squared on, so e to the negative e squared on 2, where the bottom e is 2 point. Yep. That requires me to estimate the variance of that, right? This part here, this is the sequence of precisions of the parameters. I need some way to estimate these deltas, which is how precisely to specify each of the parameters in my model. That's yet to come, but that's going to come from differentiating the model with respect to the parameters. Okay? So I haven't told you exactly how to do any of it yet, but that's where we're going. And again, just to repeat on Zara's question, as the model size gets bigger, the errors get smaller, the distribution of them gets smaller. The number of parameters increases, so the description length of the parameters increases. Okay, so I'm now going to talk about the set of parameters lambda, the parameters of the model. I'm going to shelve the initial conditions for the moment because we don't have any control over them. They just are what they are. The first thing we need to do is build a model, right? And that's the first of those bullet points. Given a model class, given some data, I want the model that gives me the smallest errors. Right? So I find lambda hat that makes my model errors as small as possible, because if my model errors are as small as possible, the description length of those model errors will be as small as possible. And that, we don't need to worry about description length at all. We can just shelve it, and we're just looking at minimizing root mean square error. Right, so you can do whatever heuristic you want to select a model from your model class. That gives you a bunch of lambda hats, which are the root mean square optimal lambdas for that model. Having chosen the best parameters of your model, I've now gone from my class of all possible models and I've plucked out one. That particular model is parameterized by a set of lambda hats. They've got some precision associated with them. What that means is that I've got my lambda hats, the parameters, but some of them maybe I'm allowed to specify rather loosely, some of them I have to specify rather exactly. How precisely or loosely I specify them will affect my model. Some of them maybe I can specify less precisely, some of them I need to specify more precisely. I need some way of calculating that precision or imprecision. That's what I'm building up to. Once I find that, then I can just substitute those deltas into, sorry Dave, I'm going to flick through several slides. I think I just flicked past it, no, here, into this expression, right? I've got my best lambdas, so I've got my errors, I can calculate that. The errors are known, n is the length of the data, that's known. K, number of basis functions, my model, well, a particular model of particular size k, I've got k as well. Gamma is a constant, don't worry about gamma. Big K and little k are the same k, that's my fault. Delta J is the precisions, which I'm going to have to find some way to calculate, but once I've calculated it, I can just sub it in there. And yep, n is the same n as over there, and this pi is the 3.14 pi, so everything's good. Everything in there I can calculate once I know my deltas. Again, Dave, close your eyes. And that gives us the description length of the particular model of size k. The schema from there is I fix the model size k, I choose the best model according to RMS error of that size k, compute the description length of that model of size k, that's my description length of my best model of size k. I then try k plus 1, k plus 2, k plus 3, and when the description length stops going down and starts going up, I stop. Okay. Questions? Anthony, you were sitting there looking, there was a question bursting out of you.
Are you sort of p-hacking it all by doing that, by trying every different k, and then...
No, it's not a likelihood p-hack. It's simply, I want to build a model of any size, and so I try building a model of every possible size. The point is that description length gives me a way of comparing models of different sizes. Yeah? So without description length, I build a model with 10 parameters and I get a root mean square error of 1. I build a model with 1,000 parameters, I get a root mean square error of 0.01. That 0.01 is not comparable to that 1 because the model sizes are different. Description length is a way of comparing the apples and oranges that are here. Putting together the RMS error with the model size in a way where you balance the two things.
Yeah.
But
Yeah, but if you were to compare models using with a description length,
yep.
you try a 1 parameter, 2 parameter model, then 3 up to 1,000, and then shows your best
Yep.
to description length. Are you, in a sense, picking the lucky one that happened to suit your data better?
It is a function of the data. So when we say best model, what we mean, here at least, is the model that is best for the data that I'm trying to build a model of. So this gets to what we were just discussing just before now, right? I mean, if you build a model that's good at predicting the Lorenz system, and then have a model that's, and then also have the model, have a single model that's good at predicting Lorenz, but also good at predicting Rossler, then the description length of that model is different depending on which task you're setting it to. Right? So it does depend on the task, but it's not really a sense of just jagging the lucky one because you did. It's a kind of greedy search across the various parameters. And we're organising in such a way that we first scan through the different Ks, different model sizes, and each time we choose a different model size, we then choose all the parameters for that gives us the best on that model size. Think of it as a grid search where K is one axis and all your other parameters are the other axis. So for each model size, you find the best set of model parameters, and then you keep going. The basic theory, which I won't flick back to, but the graph tells me that the description length should go down and then go up again, according to the hand wavy argument, which I'm not sure if I convinced Zara, but I stopped her from asking questions about it. Right.
On that
Yep.
Yeah. Each point on that you're creating by running it, and you know you throw it down just
Yep.
randomly, but you get a point. But that curve itself is smooth. Like you don't suddenly expect to jag like the lucky one that throws that curve out from its shape, right?
Correct. Partly because as we go through the increasing k process, I'm using my model of size k to build a model of size k plus 1.
Yeah.
If,
okay.
But that's an operational issue that's down here somewhere. I'm assuming that I've got some process to choose the best model of size k for each k. In general, it's not going to be optimal, it's going to be kind of approximately optimal, it's going to be a somewhat good model, and if I repeat it from size k to k plus 1, then yeah, there's going to be some uncertainty in the description length that I get, because that is the description length of a good model, not the best model, and so it's going to be a bit wobbly going down and going up again. So that then comes back to that curve that I'm drawing that goes down to a single minimum and goes up again. How do I find that single minimum when it's jagging about all over the place? Well, I have to go past the minimum far enough that I've convinced myself that I've now started to increase beyond that uncertainty. But yeah, that is all there, and I guess that maybe relates to what you're saying, Anthony.
And you redo it again tomorrow, and you're not expecting the minimum to suddenly be somewhere else. The actual curve might look slightly different.
But we hope it's in the same kind of vicinity, yeah. Yeah, I mean, you run the process once and you will maybe get 3 basis functions that do the job of 2 basis functions on the next run. So you get, the model size will vary from run to run of the whole process. I mean, there's a lot of parameters in here. It's a very greedy process. You're never going to get the global optimum. You're trying to find a good way of getting a reasonably good handle on the best model size.
Just very quick questions about the sort of like the.
You realise this is the slide that I stopped on last time, right? Yeah.
Just the first. Sorry, if you have a finger, but there's the equation that you had to start there.
Yep.
First thing we're doing.
I'll just go back to it.
That's okay. The last few terms don't actually depend on the parameters, right? So technically, they'll be the same regardless of which model you choose.
Yeah. There's 3 terms that aren't terribly dependent on the parameters. There's the one that's got an n and a gamma in it, which is effectively a cost associated with the constant mantissa of the floating point numbers. That's not quite true. No, it's a cost associated with the floor of the encoding for the error terms. Then there's the pi n one. That comes out of when you take the negative log likelihood of the exponential. There's a pi in that e to the negative e squared thing somewhere. That drops out and you can just chuck it on the side. But there are those constant offsets that don't actually affect anything. And if you're just comparing models of a fixed data set, then yeah, you chuck them away, you don't need that. Which is why, sorry Shannon, which is why if you actually run the code, it comes out as negative numbers very often. Sorry, I spoke over you.
No, I was just checking that Zara was convinced by your explanation, because I think it had quite a few people up at the whiteboard trying to figure things out.
Yeah. So is everyone happy with part 1?
I think it was just that L and E thing. That was just the thing. It was just like, I thought L and L star were the same thing.
Yeah. No. First, yeah. To say again, L star and L are quite different things. L star is just a function. It's well defined. It's got an uncertain number of terms in it, but it's perfectly well defined. L is, it's really a likelihood. It's the length of the code, but it's a likelihood.
And it's the fact that it comes from the distribution.
For the LE, it comes to the distribution.
Yeah. So you're transmitting an error of 0.111 compared to 001.
Yeah.
001 is smaller because it's coming from an error instead of collapsing into some point.
So I was just checking that they are actually recordings. I think they're supposed to be. Okay, so and the other thing to say is L star and L are different, but also L of E and L of lambda, although they mean the same kind of thing, it's the length of that code, where you go from there is quite different, because E and lambda are quite different objects. E is a bunch of random variables chosen from some distribution. Lambda is a bunch of numbers. Okay, so okay, so there's a couple of things that are worth saying here. The L star of, I think I said this earlier, the L star of lambda, you get that log, repeating logs thing. As you all know, when you take logs, things start to very slowly. Logs of logs very more slowly. Logs and logs and logs. Those extra terms change very slowly. So we're going to throw all of them away except for the first one. So when we talk about the log, when we talk about the L of the lambdas, it's just going to be, which is the sum of the L stars of the individual lambdas. We're just going to use the first term in that infinite series. Oh, it's not infinite. In that finite but indeterminate number of terms series, we're just going to use the first term. So L of theta, the parameters, is just going to be the sum of the logs of the uncertainties, the deltas of each of those parameters, and some cost, lambda, which we're going to associate with, hey, we want to specify the parameters to some fixed cost. Right. So remember, this came out of the L star expression for floating point numbers, where you had the sequence of bits and the 2 to the negative m, the mantissa part of that. I'm going to say, well, all the m's are the same size because everything is double precision floating point numbers, or 32 bits, or whatever. It's one of those numbers we get to choose because the term doesn't actually change from model to model, so it doesn't matter. And the L hat that minimizes the error is going to be, as I said, just the negative log of the likelihood of the data. So again, we choose the lambda hats using root mean square error for some model, for just a model selection task where we can just minimize error. With those optimal lambda hats, we can choose delta in a way that I haven't told you yet. But the point to take away from this slide is that given a choice of lambda hats, the question is, what are the deltas that optimize description length? Right? Optimize description length over possible deltas. Right, so fixed k, fixed lambdas, I've got that description length expression. I'm now trying to choose deltas. They're my precisions, but they're my optimal precisions. So my question is, what are the optimal deltas for that choice of lambda hats? And the rest of that is just what I was saying earlier. Once you've got that expression, LE, L theta for a particular model, then you can run through all the model sizes, choose the one that's best. Okay, so here is the nuts and bolts. Here is the bit that everyone ignores because it's a little messy. But it's also actually first year optimization. It's Taylor series expansions and setting derivatives equal to 0. So I'm going to start with, I've got some lambda hat. They're my optimal values of the parameters lambda for this particular model that I've chosen. Optimal in the root mean square error sense. Okay? I've got my lambda hats. And I'm going to ask, well, okay, having a precision delta means that I don't actually use lambda hat. I use some other value, lambda bar, which is near to lambda hat. All right? So the deltas, the precisions, are perturbations to my optimal lambda hats. That gives me lambda bar. Well, I know how to do perturbations. Well, don't tell any of the traditional applied mathematicians that because I don't know much about perturbation theory, but I know how to do perturbations in 1D. I can write down a Taylor series of that expression, h lambda, that I'm trying to optimize, the description length of the errors, h lambda bar, as a Taylor series about the optimum h lambda hat. Because this is the optimal lambda hat, the first term, the first derivative, is equal to 0. Yeah? Taylor series is h lambda hat, derivative of h lambda, second derivative of h lambda, and a term of order delta cubed. But the first term is 0 because this is an optimal value. The second term, q here, is the second derivative of LE with respect to all of the model parameters. So LE is a number, it's the description length of the error, and I'm now going to differentiate it twice with respect to each of my different lambdas, the parameters in the model. This gives me a big matrix, right? That big matrix, the ijth term of it is the derivative of the error with respect to parameter lambda I, then with respect to parameter lambda j. Okay. And it's a Taylor series, so what do I do with that q? I just multiply it by delta squared. Except because it's a matrix, I've got to do delta transpose q delta. Right? So this is just a Taylor series. It's h naught, h lambda times delta, and a half delta squared h lambda's second derivative. Now, if I want to, so that's h lambda bar, that's my approximation to LE. I want to write down Lx theta. I need LE, the bit inside the big parentheses, and I need my expression for the model parameters, L theta, which is going to be approximated to first order with the first derivative. So this is the L stars. The second term here is the L stars, but I'm only using the first term of the L stars. Okay? So that's my approximation for my model description length as a function of deltas. Now, this is where the next use of optimum comes in. I want to find the best deltas. So I want to find the deltas that optimize this expression, this Lx theta expression. Okay, there's a lot of optimizing going on here. But it's a second it's an optimization over delta, whereas the first line is assuming an optimization over lambdas. Okay? Now, if I want to optimize this expression over deltas, well, as a function of a single variable, delta, how do I find the optimum of a function of a single variable? I take the derivative, set it equal to 0. So what's the derivative of all of that? Well, the derivative of that one with respect to delta, there's no delta there, it's 0. That one's 0. That one is... it's in the right place here. Yeah, I'll use my fingers. I was trying to... so the first term, h lambda hat, derivative of that with respect to delta was 0 because the lambda hats were chosen with respect to root mean square error and nothing to do with the delta. 0 is derivative of 0. Delta t q delta, that's delta squared. Derivative of that is just going to be q delta. That's q delta. Order delta cubed, we're going to throw that away. And the other term just gives me log of that, gives me the 1 on delta, negative 1 on delta, which leaves me with this expression here. All right, this expression here. What's up, Dave?
No, it's just painful.
This expression here, yeah, this is number 6. Equation 6 is all the very worst parts of my PhD. Equation 6 is, I've got a vector, delta. Delta I is the ith component of that vector. Delta is that whole vector. Q is a matrix. That matrix is the second derivative of the model with respect to the, or second derivative of the model prediction errors with respect to the model parameters. So I've got a matrix times a vector. That thing is a vector. So the ith component of this vector is equal to the ith component of this vector. Anthony, what we talked about this morning, the tricky part here is if that's the second derivative of your reservoir with respect to the reservoir weights, that's 1,000 by 1,000, and you've got to find deltas that satisfy that equation. That's number 3. That's your third chapter. Okay? So, easy. I've got an equation I can solve. All I need to do is compute this Hessian, this Q, plug it in, and numerically do some jiggery-pokery and solve it. So how do I compute Q? Well, in terms of notation, I'm going to change the way I write everything because it will make things slightly less painful. Okay. And what I'm going to do is replace the expression for the model on the top line, fx, with the vectorized version down the bottom here. Okay. What I'm going to tell you is that the model errors, up to some messing about with indices, which is what it says in the text there, the model errors are the next step in my data vector minus the model. The model is this matrix V, get to that in a second, and my model parameters, the weights. V is the evaluation, is a matrix. Each element of that matrix is the evaluation of one of the basis functions, one of the phi's in my model, at one of the data points x. Okay? So think about which way around is it v lambda, so so each column of v is the evaluation of a single basis function across all of my data. So basis function 1, all of my data, basis function 2, 3, 4, and then multiply with them the lambdas, so I've got lambda 1 times the basis function at all the data, lambda 2, all the data, So I hope by waving my hands about, I'm convincing you that we can work with this equation rather than that equation. The biggest approximation here, the second biggest problem with my PhD, is that I've just ignored all the CJs and RJs. I've assumed the only parameters I care about are the lambdas. If you want to know how to deal with the CJs and RJs, read my PhD. And then fix all the bugs that I left in there deliberately for the readers.
They're not in V.
They're in V, but in the next step I've taken the parameters that I care about lambda out, so that when so I'm going to differentiate, I want to get the second derivative of E with respect to the model parameters. And I'm writing it in such a way which all the parameters inside V have just been magically hidden in the closet, and I've just got the weights, the lambdas outside them.
Why is that a problem? Like, why did you say that? I feel like that's sort of, and then like you have to do that.
But then I'm going to say, well, the second derivative of this E with respect to the model parameters is just with respect to the parameters lambda, and none of the parameters C and R. And this is the way that Kevin and Alistair did it in their on selecting models, blah, blah, blah paper. I was then tasked with figuring out what happens if you actually include the C's and the R's in that calculation. And the TLDR is you get a mess and it's impossible to solve it. Well, it's difficult to solve it. Does that answer your question? Or? Okay, so now I need the second derivative of this E with respect to model parameters. I can rewrite the description length in terms of, so this is the model parameter term. The L theta is the model parameter term. The negative log PTET is the negative log likelihood, but now I'm writing it down explicitly in a way which I hope you can see where the calculation comes in here. The PET is the probability of my actual observation ET given my assumed distribution Gaussian of some standard deviation. Right, so if I've got a Gaussian mean zero standard deviation 1 and my error observation E is 0, then that's a very likely outcome and the description length is short. If my number is 6, then that's a much less likely outcome, and under that assumed distribution that I'm coding on has a much more costly expression. I haven't chosen the variance of that Gaussian distribution yet. That's the sigma squared here. But the first term, the negative logs thing, will just be n log 2 pi sigma squared, and the L theta term, well, the second term in the second line comes out of the negative log error term as well. Right, that's just E transpose E. That's my total root mean square error. So it's E transpose E over my unknown but to be determined optimal variance for the error distribution I'm going to assume. And the last term, L theta, is just L theta. It's just left there. So this is the thing that I need to differentiate twice with respect to model parameters. Dave's looking smugger and smugger up the back there. Yeah, I've got e to the minus e squared on 2 pi sigma squared. Yes, I know. That is in everywhere. But it's a slightly different script e when it's the... Okay, so how do I do that? So now if I want to differentiate Lx theta, this whole thing, with respect to the model parameters lambda, right? Well, first of all, the first term, there's no lambda there, so differentiate with respect to lambda, it's nothing. The third term, there's no lambda there, differentiate with respect to lambda, that's nothing. The middle term, the bit where the lambda is in here, so I have to worry about differentiating this with respect to lambda. Except I am skipping over the fact that the sigma squared, the variance of my error distribution, is also an unknown parameter which I need to specify, and it needs a precision of its own, so that actually does the calculation as well. Differentiate that with respect to the lambdas, and I get the expression on the top line. The optimal value is, so I can find that lambda hat is that thing there. Differentiate again, differentiate with respect to delta squared with respect to the sigma squared. Do the algebra, and I'll leave you to do it because I think I've got a meeting with Hector right now, right? I think I've got a meeting with one of the honours students who's not here. This thing, it comes out to just the surprising result that the best value of sigma squared is actually E transpose E on n, which is kind of reassuring, right, Samson? Yep. You happy with that? So that gives me a way of constructing my Q matrix, right? This big Q matrix, just different derivative with respect to each of the parameters. I'm ordering them so that sigma squared's on the end. So the first top left block is the derivative with respect to each of the lambdas twice, which turns out to just be V transpose V, which is why I wrote it in this form. The second derivative with respect to the lambda squared is just this yucky looking expression there, which is just the variance. And the cross terms haven't quite gone away just yet, except that because these lambdas are optimal, this one is 0. So the cross terms, the lambda delta squared and delta squared lambda disappear. So I've got a block diagonal matrix with a lambda lambda block and a sigma squared single number. No one's objecting? So my Q is just that. My Q is nice and simple because I'm just looking at the pseudo-linear lambda weights, and I'm ignoring all the r's, the radiuses and the centres of each of the basis functions. So you can see, Shannon, if I included all those other derivatives, that would be quite a bit more mess. And V, again, is just the evaluation of each of the basis functions at each of the data points. So that's the big matrix of the state of your network, or the state of your reservoir, the state of your basis functions at all time. You just multiply that by its transpose, get your dimensions right, and then you get equation 8 is the Q delta equals 1 on delta that you've got to solve to get the optimal values of the model precisions, the deltas. It turns out that the equivalent equation for the bottom right-hand corner I'm calling the delta for my sigma eta, because I'm running out of Greek letters, and the optimal eta is the solution of this scalar equation, which means it's that, which again, I think even the Bayesians amongst us will be kind of happy with that as a precision for a variance. It's got an n there, so it's, everything in statistics scales like the square root of n, right? So it's got the right number.
Is that, sorry, so e to the precision
Of this variance of the noise. So I'm saying that the variance of the noise that I'm using to describe the errors is actually a parameter of my model as well. So I need to specify that variance and a precision for that variance. The precision for that variance is the eta, which is a point estimate of the variance itself, which is why it goes like 1 on square root of n, I think. Then things get easy. Basically, chuck all of those things into the original equation for L, x, and theta, do a bit of stuff, and you get down to, at the very bottom, the equation that I started with at the very top. I'm going to leave that equation in that form, give you the PowerPoint, or the PDF, and you can go and work through that for yourselves if you're still worried about believing me on that one. Because I think that just about brings me to the end here. That's the equation I started with. And for comparison, well, there are other information criteria that I could have used instead of description length. One of them gives an expression like that. The other one gives an expression like this. Both of those expressions are quite a bit shorter than the description length. Say that again. AIC and SIC are much shorter expressions than the minimum description length expression, somewhat ironically. But the advantage of the description length expression is that it includes the precision of the parameters. Right? The AIC and SIC treat all parameters like they're important. They treat every parameter in your model as equally important, and the number of parameters matters. This is obviously wrong, because I can just add a parameter k times 0, or rather, so lambda k times 0. Yeah, a new parameter in my model. Lambda k plus 1 times 0 too. Lambda k plus 2 minus lambda k plus 1. I can just add parameters as much as I like, and they're meaningless. And this is the problem with machine learning. When you talk about having a large language model with 15 billion parameters. Well, you do, but you're not actually using 15 billion parameters, which again, Anthony, is description length of the reservoir. You can say, well, actually, how many parameters actually matter in the model. And I think that's it. Oh yeah, that's just a recapitulation of my roadmap, and that's the end of the story. So just to repeat one final time, everything now is computable. So I choose first of all some model class. Here it's radial basis functions, sum of lambda theta, lambda phi's. Can be whatever you want. It helps that the parameters are linear in the model class. Otherwise the calculation gets a bit messy. Anthony, you need to learn the chain rule. Find the best model in terms of those model parameters. That's the lambda hat. Given lambda hat, choose delta by solving the Q delta equals 1 on delta. That requires you to compute Q. Q is just V transpose V. So you've got your deltas. That gives me the description length for the model of size k. Rinse and repeat for different size k's. Find the size k that serves me best. The end. Simple. Questions? I've got absolute stunned silence. Okay. If there are questions, I'll come back and do part 3. If there are questions, let me know what the questions are. I'll give you the slides so you can work through the details at the end, which was too much algebra for me. I think the slides are now correct. I did check them all again, and I did remove a couple of errors. So hopefully now you all know how to do description length.